Alright, Physics 11H, or AP Physics C. I'm going to go through the midterm review sheet. I don't have my my better video recorder here at home. Forgot to bring home the nice one Mr. Roboto gave me. So I'm going to do my best here. Zooming in a bit. It's a little bit blurry, but should be doable. Alright, here we go. Alright, does the acceleration of the object appear to be 0 anywhere? If so, at what time does it appear to be 0? How do you know? Alright, appears to be 0 right about there. Acceleration's where the slope of the line is 0. Alright, that appears to be about 5 seconds. So, acceleration is 0 at 5 seconds. Because the slope of the tangent line is 0. Proved by differentiation. Alright, so A equals dV dt. Great. Let me see if I can focus this a little bit better. I'm zoomed in, so it might not. No, that's because it's going to get just pixelated from zooming in. The derivative of this with respect to time. Alright, so negative 6t plus 30. So where the slope of the line is 0, so we solve for putting 0 for A. Equals 6t plus 30. Bring this over here. 6t equals 30 divided by 6 divided by 6. T equals 5 when the acceleration is 0. Alright. Determine the displacement of the object between 2 and 5 seconds. Alright. Displacement, delta x equals the integral from, this is from 2 to 5, so this is a little bit different, right? Of negative 3t squared plus 30t plus 20 with respect to time. Alright. Now, sorry, got a stool here. I can't see the screen, so I gotta rely on this. Be in the right position. Let me just double check. Yeah, okay. So, take the antiderivative first. So, negative 3t cubed over 3 plus 30t squared over 2 plus 20 evaluated from 2 to 5. So now, this is where it gets a little bit different. We've always had 0 for the bottom here. So for this one, it's actually 2 on the bottom. So it's negative 5 cubed plus 15 times 5 squared plus 20. That's that. Then I have to subtract off what happens when I plug in 2. So negative 2 cubed plus 15 times 2 squared plus 20. Alright, then we do the math. So plug it all into the calculator here. Negative 5 cubed plus 15 times 20. Oops. Where's my other calculator? Oh, I don't have my good one here. Negative 5 cubed plus 15 times 25 plus 20. That gives us 270. 270 minus 2 cubed plus 15 times 2 squared. I just did it again. Negative 2 cubed. 4. That is 72. 270 minus 72 is about 198. Now let's see if that makes sense. So it's from 2 to 5. So it's from here to here only, right? So let's just see if this makes a little bit of sense. All right, so if we can approximate this, right? Sorry about that. from 2 to 5. We can approximate this. So 1, 2, 3 seconds times 70. 3 times 70 is 210 meters. 1/2 base times height from here. That would give us approximately 1/2 of 3 times about 20, right? Geometrically. 60, 30, so I get about a total displacement of about 240 meters. So, reasonable. No, not so reasonable actually. Probably made a math error here somewhere, right? 3 times 70. So I could go back and check that really quick. -5 cubed plus 15 times. Alright, just found my problem. I forgot the T on this 20T. Alright, that makes this 350. That makes this. So it's 20 times 2. 20 times 5 here. So that's going to be bigger too, though. So -2 cubed plus 15 times 2 squared. I keep putting this in my calculator wrong. Oh, -2 cubed plus 15 times 4 plus 40. All right, minus 92. So 350 minus 92 is about 260. 260 meters, much closer to what I calculated up here. So that's probably a good answer. Sorry about that. So don't forget that T there. I forgot the T. I've done that a couple times actually. Average acceleration of this object over the whole time arrow, A equals delta V over T. Average acceleration. It doesn't say instantaneous. So the change in velocity here is -20 meters per second in about, I don't know, 10.5 seconds. Which is 20 over 10.5. It's about 1.9. -1.9 meters per second squared for the acceleration. Alright, finally, done with the first question. It's all going to go uphill from here. Got to save those to scan for you later. Alright, so on to number 2. An object is released from rest so that its position function is as follows. Until the object reaches terminal velocity. So it's -2 cubed plus 14t squared. Where x is in meters and t is in seconds. The object remains at terminal velocity for the remainder of its motion. Alright, so v is constant once you get to terminal velocity. Determine the time it takes to reach terminal velocity. Alright, so with this one, what we got to do is we got to take a couple derivatives here, okay? v equals dx dt. Alright, the derivative of that with respect to time. So t3 comes downstairs, so -6t squared plus 28t is the velocity function. Then acceleration equals the derivative of velocity with respect to time. So we take a derivative again of this now. So we get -12t plus 28 is the acceleration. And it's v terminal when a equals 0. So therefore we take that information, we say a equals -12t plus 28, and we solve for the time. So 12t equals 28 divided by 12 divided by 12. 28 divided by 12 is 2.3. So the time to terminal velocity is 2.3 seconds. Cool. All right. So again, terminal velocity when acceleration equals 0, it's not gonna change velocity anymore. So the object, what is the object's terminal velocity? Well, we take that time now and put it back into the velocity function. So the velocity at 2.3 seconds is -6 times 2.3 squared plus 28 times 2.3. So -6 times 2.3 squared plus 28 times 2.3. It's about 33. So v term is 33 meters per second approximately. Great. Now down here, sketch on the axis below qualitative velocity versus time graph for the object, including motion for some time after the car reaches terminal velocity. Indicate the time where the car reaches terminal velocity with the vertical dashed line. So V and T, all right, this would be at that 2.3 seconds. You know, it says qualitative, so you don't really need that. And I know after that, it's going to be constant, right? So now, you got to think about how this line is shaped, right? Does it just go up like this? Does it go up like this? Typically, it just kind of goes up like this, but we can look at our velocity function here, right? Negative 6t squared plus 28. So at t equals 0, the velocity is 0, so it's got to start down here. All right. We would have to be careful of that. If there was a term here like plus 10 or something, then you'd have to start your line farther up. It's not going to be on the midterm, but that's something important to note. All right. So how does it move? Well, I know at the end here, you know, I could look at the acceleration, tell me what the slope of the line looks like. So at t0, I got to have a big positive slope, right? At t equals 0, a equals positive 28. But as time goes on, it has to decrease. So we start off with a positive slope, and then it levels off. Okay, and that's number 2. All right, just gonna try to go as fast as I can here. Here we go. Here's a little projectile motion. You throw a ball from a 60-meter high cliff with an initial velocity 25 meters per second at an angle 10 degrees below the horizontal. Assume every instance no during time it takes to hit the ground. All right, so I always draw a picture. All right. The horizontal is that line, so V initial is directed at 10 degrees below that line at a speed of 25 meters per second. All right, so it's an angled quantity, so I'm going to go ahead and find the V initial V naught x is going to be actually 25 times the cos of 10, which is going to be 25 times the cos of 10. Make sure you're in degree mode. About 25 meters per second. Small angle approximation we'll talk about later on. It's about 24.6. V naught y is 25 times the sine of 10. It's going to be something small, but it's not going to be insignificant. 25 times the sine of 10 is about 4.3. Now that's the interesting thing here. When you do two sig figs, pretty much the cos of the angle is pretty much 1 if it's 10 degrees and below, if it's what we call a small angle. And again, I'm sorry for the blurriness here. Hopefully that doesn't hinder your viewing experience. You can see it's not bad as I get. It's because of how far away I am and the zooming in that's happening here. So time it takes to hit the ground. So that's going to be the vertical direction, right? I know it's 60 meters, it's got to fall down. So delta y is going to be negative 60 meters. So delta y equals 1/2 ay t squared plus v naught y t. All right, so negative 60 meters equals 1/2 ay is negative 10 or negative 9.8, whatever you want to do there, meters per second squared. Time, don't know. And v naught y, though, is negative 4.3 meters per second times time. So again, I don't know how long it takes to hit the ground, but there's a problem here, right? Usually v naught y is 0, right? Oh shoot, I don't know if I know how to do this on this calculator. But what we're going to do is we're going to write this like a quadratic. We're going to drop those units. We're going to do 0 equals negative 4.9 t squared minus 4.3 t plus 60. We're going to solve for the roots of t. All right, so this has a poly solver. We'll see. You can go ahead and plug in the coefficient. So a is negative 4.9. B is negative 4.3. C is 60. Solve. And it's doing it. We've got, it's giving me a couple different roots here. All right, it's giving me time 1. I'm going to write this down over 3.1 seconds. Negative 3.9. So it must be the 3.1 seconds, right? And if you're not convinced of that, go ahead and plug it in, right? Negative 4 point, like that poly function, I'm not sure I love that. 4.9 times 3.1 squared minus, I remember doing this, back in the day, solving this. I was like, wait a minute, do I believe what the calculator just gave me? All right, let me plug it back in and see what I get. And you get almost 0, right? So 3.1 seconds is going to be good enough for me. You could always compare it against, too, just dropping something from a height of 60 meters. So if this term wasn't here, right? This term wasn't here, and you solve for time squared, it'd be second square root of 2 times 60 divided by 4.9. I know some of you do this kind of thing, right? Like you develop it in your test taking. So if I didn't have that little vertical component, it would take about 5 seconds for this thing to hit the ground. 60 meters is pretty tall, right? That's part of it. 60 meters is pretty darn tall. It's like a 6-story building, right? So if there was no initial velocity, it would have taken 5 seconds. So 3.1 is reasonable. How far from the edge of cliff will land? Delta x equals 1/2 at squared plus v naught t, v naught xt. Again, x acceleration is 0. So delta x is simply 25 meters per second times 3.1 seconds, which is going to be about 75, right? Let's just see what the decimal is. It's going to be 75.25, I suppose. Oops. 25 times 3.1, 70, oh no, 77.5, so we'll go 78 meters. 78 meters on that. All right, next one. Disc rotates with an angular velocity function as given below. I'm just going to put a note here. Use calculator. All right, solve function. It's up to you. Use calculator. Disc rotates with the angular velocity function as given below. Determine the angular acceleration at 3 seconds of rotation. So angular acceleration is alpha equals the derivative of velocity with respect to time. I tell you what, sometimes it's easier to just like not include the word angular. And just read it as velocity and acceleration, right? So determine that with disc rotates with a velocity function as given. Determine the acceleration at 3 seconds. So derivative of this function with respect to time is negative 4t squared plus 6, right? That's it. Plug in 3 seconds, so acceleration at 3 seconds equals negative 4 times 3 squared plus 6. So negative 4 times 9, that's negative 36 plus 6 is negative 30. Negative 30 radians per second squared. So be careful of the units. I should probably make a note here that this would give units of radians per second, right? Determine the angular displacement in radians of the object after 5 seconds of rotation. So angular displacement, delta theta, equals the integral from 0 to 5 seconds of negative 2t squared plus 6t plus 3 with respect to time. So to solve the integral, we take the antiderivative first. So negative 2t cubed over 3 plus 6t squared over 2 plus 3 times t from 0 to 5. I remember making that mistake in a previous video I've done for this class. It's really embarrassing. But anyhow, evaluate it from 0 to 5. I know it's just plug in the 5 here. So negative 2 times 5 cubed over 3 plus 3 times 5 squared plus 3 times 5. All right. Negative 2 times 5 cubed divided by 3. Oh, you jackhammer. Negative 2 times 5 cubed divided by 3 plus 3 times 25 plus 15 equals 6.7. delta theta equals 6.7 radians. It's about 2 rotations or so. Or wait a minute, no, 2 pi. So it's about 1 rotation. All right, and technically this is minus 0 if you put in 0 here, but usually we just go like that. All right, so there's that one. All right, force setup. All right, let's go. We got to set up a ball of 3 kilogram mass is attached to 2 strings and resting on a 35-degree incline. Plane, the vertical string applies a force of 6 newtons to the box. Determine the normal force acting on the box and the force of tension that the string parallel to the plane applies. So we're looking for the normal force, magnitude of the normal force, and magnitude of the tension of that string. Include a force diagram. All right, so forces. Let me draw them right on the picture first, right? We're going to have F1, Ft, we'll call that. Tells us that, right? We'll call that F1, F2. We're going to have the force of gravity also going straight down, Fg. All right. We got to assume it's frictionless, right? Because we don't know anything about the coefficient of friction. So I remember that now. Kids asking that, and oh yeah, I got to update that, and then I forget to update it. Any other forces? Yep, Fn. Fn. Now this one's interesting because how do you want to draw it, right? Do you want to put the normal force and F1 on the axis, or do you want to put the up and down forces on the axis? So this one's a wrinkle. It's kind of a wash, right? Because when you think about it, we might actually want to put Fn and F1 on the axes, right? Because then we don't have to write them in terms of components, because that's what we're looking for. All right, so this is a little bit of a different type of question, right? Where it actually kind of illustrates why this is F2, why sometimes you might actually want Fg. I'll call this Fn, and perpendicular to that is going to be F1. All right, so this one, either way, you're going to get 2 forces on the axis. So if you make it on an inclined plane like this and like this, then you got to find components of F2 and G. If you put it with Fn and F1, then you're going to solve for those directly, right? So I'm going to do it like that. I am going to put it with the plane because I want F1 and Fn to be on axis, right? I want those to be on axis. All right. So now F2, so here is theta of the ramp, 35 degrees. That's going to be over here, right? It's going to be that angle there is also going to be 35 degrees. So there's our force diagram. Let me break it into x and y components now. So, we're going to have F2x going that way, F2y going this way. We're going to have FGY going that way, FGX going that way. It's F2x. This is hard to see. F2y, FGY. All right. All right. Now, all right. So let's break Ft into x and y components. So Ftx here is going to be 6.0 newtons times, well, it's going to be the x is going to be the opposite side here, right? The opposite side. So it's going to be 6 newtons times the sine of 35. That's going to equal 6 times sine of 35, about 3.4. Ft, or I'm calling it t, it's F2. F2y is going to be 6.0 times the cos of 35, which is going to be about 4.9. All right, and then I also have to find Fg. So Fgx is going to be mg, which is about 30 newtons, and the x is going to be the opposite side, so it's sine of 35. 30 times sine of 35 gives me, getting out of frame here a little bit, gives me about 17 newtons. FGY is 30 newtons times the cos of 35, which is about 25 newtons.